Hello everyone. So this is a question from JEE Advanced 2026, paper 2. The correct statement regarding the periodic properties of elements is second ionization enthalpy of carbon atom is less than that of boron. Okay. Increasing order of ionic radii is this. Okay. Under identical conditions in solid state, density of potassium is more than density of sodium. Okay. The HH bond is weaker than FF bond. Okay, so the chapters involved is classification of elements as block and chemical bonding. Okay, so to start with, we need to know what are periodic properties. So these are properties which are related to the electronic configuration of the elements. Okay, so they are related to electronic configuration of the elements, and they also show regular gradation, that is regular or gradual change when we move from left to right in a period or from top to bottom in a group. So they show gradual change when we move from left to right in a period or top to bottom in a group. Okay, so let's look into the options one by one. Option A says that second ionization enthalpy of carbon atom is lesser than second ionization energy of boron. Okay, so to compare this, we have to know their electronic configuration. So for carbon, it is 1s2, 2s2, 2px1, 2py1, and for boron, it is 1s2, 2p, sorry, 2s2, 2px1. Okay, so for the first ionization enthalpy, we have to knock out electron from 2py in case of carbon and 2px in case of boron. Okay, so I will use arrows, and to knock out or to find out the second ionization energy, we have to knock an electron out from 2px in the case of carbon and from 2s in the case of boron. Okay, so this is important. Okay, we know that electron of s orbital has the maximum probability of being found near the nucleus, right? So s has the maximum probability of being found near nucleus. Okay, and this probability goes on decreasing in the case of p, d, and f, right? And it keeps on decreasing in case of p, d, and f orbitals of the same shell. So therefore, within the same shell, very important, penetration effect decreases in the order s, p, d, f. Okay, and if the penetration effect of electron is more, it will be closer to nucleus. If penetration effect of electron is more, it's closer to nucleus. And if it is closer to the nucleus, it will be held more firmly by the nucleus. So therefore, ionization energy will be high. Okay, so therefore, ionization energy will be more to knock out a s electron than a p electron of the same shell, because s has more penetration effect compared to p. So therefore, second ionization energy of boron is more than second ionization energy of carbon, because in the case of boron, we have to knock out an s electron, and in the case of carbon, we have to knock or remove an p electron. As you can see, in the case of carbon, we have to remove a p electron, which has comparatively less penetration effect compared to b, where we have to knock an electron out from 2s, where the penetration effect is high, spends more time near nucleus, and hence more ionization energy required. So therefore, yes, A is a correct statement. Then we have statement B, which says that increasing order of ionic radii is Al plus 3, Mg plus 2, and then Na plus. Okay. So clearly we can see Al plus 3, Mg plus 2, and Na plus, they contain 10 electron each, all three of them 10 electron each. So therefore they are isoelectronic species. Okay, and ionic radii of isoelectronic ions decrease with the increase in magnitude of nuclear charge. Very important. Ionic radii of isoelectronic ions decreases with increase in magnitude of nuclear charge, or you can say that as nuclear charge increases, the size decreases. Okay, so this is because as power of the nucleus increases, it holds the outermost electron more tightly, resulting in a decrease in size. So it will pull this more. So because of that, there will be contraction in the size. Okay, so the given order is, so this is correct, because nuclear charge of Al plus 3 is plus 13, nuclear charge of Mg plus 2 is plus 12, nuclear charge of Na plus is plus 11. So therefore size of Al plus 3 is least and Na plus is the highest. Okay, so therefore B is a correct statement. Cool. Then we have to talk about statement C. Statement C says under identical conditions in solid state, density of potassium metal is greater than density of sodium metal. Okay, so as we move down the group from lithium to cesium, both atomic size and atomic mass increases. Okay, but increase in atomic mass more than compensates the bigger atomic size. So the point is the increase in atomic mass is more compared to the increase in size. So therefore density of alkali metals increases from lithium to cesium. So therefore density of alkali metals increases from lithium to cesium. Okay, but there is an exception. For that we need to see some values. So we have lithium, sodium, potassium, rubidium, cesium. So the size is 152 pm. For sodium it is 186, potassium 227, for rubidium 248, for cesium 265. Okay, and the difference in their size is, here it is 34, here the difference is 41, here the difference is 21, here it is 17, and the density of lithium is 0.53, sodium is 0.97, potassium 0.86, rubidium 1.53, and cesium 1.9. Okay, so can you see there is an abnormal increase in size of potassium from sodium. So sodium size is 186 picometer, potassium is 227. So there is a very high increase in size, 41, okay, which is more than the increase in mass from sodium to potassium. So therefore density decreases from sodium to potassium. Okay, so therefore density of potassium is less than density of sodium. So therefore the statement C is incorrect. Cool. Then we have statement D. It says that HH bond is weaker than FF bond. Okay, so to compare their bond strengths, greater the size of the atoms, greater is the bond length. Greater size of atoms, greater is their bond length, obviously, and less is the overlap because of their huge size. Therefore, less is the bond dissociation enthalpy. So, fluorine has size 72 picometer, is bigger than hydrogen whose size is 37 picometer. So therefore it is easier to break a FF bond, easy to break FF compared to HH, right? Also, greater the number of lone pairs of electrons present on the bonded atoms, greater is the repulsion between the atoms. Very important. Greater number of lone pairs of electron on bonded atoms, more repulsion, and obviously less is the bond dissociation enthalpy because it is already unstable because of the repulsion. So very less energy is required to break it. Okay, so if you look at fluorine, it has 6 lone pairs compared to HH, which has 0. So therefore it is easier to break FF compared to HH, and it is also supported by experimental values. The bond dissociation enthalpy of FF is 139 kilojoules per mole, and in the case of hydrogen it is 436 kilojoules per mole. Okay, so therefore statement D is incorrect. Okay, so therefore the correct statements are: A is correct, B is also correct, C is incorrect, and D is also incorrect. So the correct answer is A and B. Okay, thank you.